Good afternoon. This is the second part of our design discussion on robust design, and this is continuing from the previous lecture, lecture number 33, that was on the basics of Taguchi methods. What we'll be doing now is discussing the method for achieving a robust design. That's what we'll be illustrating in this particular lecture. Before I go further, let me just tell you something about the notation that is used commonly. Generally speaking, most of Taguchi's experiments, those are based on orthogonal arrays. Orthogonal arrays, OAs in short, those are given in matrix notation, and the notation is usually written like this: L n and then bracket 2 to the power k. And these are actually, let me just explain what these are. L is of course the notation of the OA matrix itself. Number of runs are specified by this letter n. The number of factors, those are specified this letter k, and the levels that you'll use for each of those factors, that is denoted by what we call 2, this number 2. So that's actually L n and in bracket 2 to the power k. That's like one notation that's used for orthogonal arrays. There's another array, another notation that is also used, and sometimes of course we've got something associated with each array, each OA, that is called the linear graph of that particular array. For example, look at the triangle on the left. It is showing here columns for certain it has got certain nodes and certain branches. The arcs and nodes both specify the mark of the column. So there is one node that is specifying column number 1, and another node is specifying column number 2. Then between them we've got column 3 assigned. Similarly, I've got column 4 here and column 5. What this is really saying is the interaction of some factor that I've assigned at column 1 and another one at column 2, the interaction between those two will be noticeable in column 3. Similarly, if I've assigned a factor at column 1 of the orthogonal array and another factor at column 4 of the orthogonal array, then column 5 of that array is going to represent the interaction between 1 and 4. Similarly, the interaction between factors 2 and 4 would be found by doing calculations using the data, using the notations in column 6. Column 7 stands by itself, and I can use that. So here I can study the interaction of 1, 2, 3 factors with each other. That's like 3 different 2-level factors. This column is standing by itself, and I can assign another factor there to conduct my experiment. So in all, I'll be able to study 7 factors. Out of those 7 factors, basically I'll be looking at 1, 2, 4, and 7 as main effects. 3 is actually an interaction effect between 1 and 2. 5 is the interaction effect between 1 and 4, and 6 is the interaction effect between 2 and 4. That's how it is done. I could do the column assignment slightly differently. If I assign factor 1 to column 1, factor 2 to column 2, factor 3 to column 4, factor 4 to column 6, or A here, B here, C here, D here, I'll be able to study the interaction between A and B by looking at column 3, and so on and so forth. So these are like linear graphs that make it easy for us to recognize where the interactions are going to be. And thereby I can do my calculations to find main effects and also some interaction effects. There is clearly a correspondence between the classical 2-level factorial designs and Taguchi's design. Taguchi's designs have just been popularized by Taguchi. That's why they are called Taguchi matrix. They are identical to classical matrix. And Taguchi has provided some additional matrices also. That's what one of the things Taguchi has done. And I picked it up from a book which is there, the Design and Analysis of Experiments book by Douglas Montgomery, 1997 edition. If you look at page 631, it will show you this representative there. And of course, there are a large number of other arrays which are also useful. They're also useful as for running Taguchi experiments. And something we got to remember is, remember we were not looking at interaction. Therefore, Taguchi arrays are basically screening designs. They basically let you see very quickly which factors are important and which factors are probably not so important. That is something that can be done quite easily using orthogonal arrays. I assume when I'm using Taguchi's arrays, I assume that most of the interactions are either small or they are not present at all. And it does not guarantee that we get highest resolution design. That means we are not able to see a lot of interactions that also should be in some cases important. Let's move now to this concept of robust design. Something I've got to tell you is, when we are talking about robustness, we are talking about variability of response. And we got to remember that this variability is produced not because the design variables are floating all over the place, but because environmental factors, these are the factors that we are not controlling, they are impacting on the system and causing it to vary in terms of its performance. That's like something that is happening when I'm using the product out in the field under the influence of environmental factors only, in addition to, of course, the design factors which are there. When this is happening, what I have to do is, to create a robust design, I have to somehow conduct experiments that look at the variations done on the design variables and also variations done on the noise factors, because the two together, they really determine the total effect, the total response. The total response is partly controlled by design variables and partly by the environmental factors. What we have to do is we have to choose these design variables in such a way that the system becomes insensitive to the effect of noise. That's something that we have to do. If we are able to do this, we will end up with a robust design. Let's see how we do it. What Taguchi suggested was that you construct two arrays, two matrices. One will be the inner matrix, that's the green matrix. The green matrix is inside, the big box. The big box is the design matrix. This is the one that has got I1, I2 and I3, three design variables. And with that, we are able to basically generate 8 different types of prototypes if each of these factors is basically looking at 2 levels. If you are manipulating these different design factors at 2 levels each, I'll end up with these 8 possibilities. 2 cubed, that is 8. That's the construction of the inner array. The outer array, basically what it does, it brings in noise now, also in a controlled way. So here we've got 2 noise factors. In this particular example, we've got 2 noise factors, E1 and E2, they are the environmental factors. And with them, I'm able to generate, if they are at 2 levels each, I'm able to generate a little square. That's like a tiny matrix that will try to shake this prototype. The same matrix I'll be using here. So here what I'm doing is, I've got a product, I've got a prototype, and I'm going to be shaking it. I'm going to be shaking it with the environmental factors. So if I've got a product in my hand, I'd try to impact it using environmental factors, which in this case could be a physical force, it could also be temperature, it could be dropping it, and so on and so forth. Any of those things, even the quality of the components, those could be considered to be noise factors. When I bring in design factors which are inside, and I impinge it with environmental factors, the variance of this the response of this is going to vary. I have to discover such a design which will be one of these prototypes. See, there are 8 prototypes here. Prototype 1, prototype 2, prototype 3, prototype 4, prototype 5, 6, 7 and 8. One of these is most robust, and that's what I have to discover. For that, what I have to do is I have to shake these prototypes, each of them, with comparable noise conditions. When I do that, I'll be able to find the prototype that's going to be the robust one. And that's the one I'll try to commercialize. Let's see how this is done in real life. We have a situation here where we are trying to, this is like starting your car early in the morning, when your battery hopefully is fully charged. And of course, that voltage, the voltage of charging and the voltage of the fully charged battery, if it is used for a while, it will be partially charged. In fact, that's going to reduce its voltage. Then, of course, I've got ambient temperature. You know very well, on cold days, when the temperature outside is cool, it's not very easy to get all the juice that you want from the battery. But the starter motor it better crank, I better turn the full engine with all its might. And that should happen with minimum sensitivity to two things. One, the battery voltage within some reason, and also ambient temperature within some reason. If you're able to do this, you've got a good starter design. What did they do? They had three design variables: armature turns on the starter motor, gauge of the wire used, and the ferric content of the core. These were three design variables that they could play with. They wanted to get a good starter motor design. They wanted to reach a good starter motor design. And as far as the environment was concerned, battery voltage would be one, which could be at two levels, low and high, and ambient temperature also would be low and high. Then they built one prototype which was at low level of I1. I1 is one of the design variables, armature. I2 would be gauge of wire, also kept at low level, and the ferric content of the core, that was also kept at low level. They ran this trial and they made sure that while these results were evaluated, the motor itself, the motor that you produce, the prototype itself was subjected to these noise conditions. So I took the same thing and I measured its torque at these different conditions. Under certain conditions it gave me good torque, in certain conditions it gave me poor torque, and I calculated the mean of these responses for each of the noise settings and also the standard deviation of the responses. Notice something here. In the conventional design task, I would have just probably looked at the mean. I would have found probably the highest one, and that would have been the one that I would have recommended for basically for commercialization. But it turns out that such a thing would not be really a robust design. The robustness could be further improved because the standard deviation here was 14.7. If I look at another prototype, the torque is slightly less, but it's much more robust. It's 14 here and 8 here. That's almost like half of it. So in fact, it turns out that the standard deviation of the output turned out to be much smaller here. This, of course, I could plot. And I could find the optimum settings for this, and I could do that by doing these things. And I'll try to show that to you in a minute. I'll show that to you. Couple of other things Taguchi did. He said, you run your trials, you've done your trials, you got the data. Let me show you data analysis method. And of course, here there's a bit of controversy in the way Taguchi approached his data analysis method. Taguchi, being an electrical engineer, he went after signal to noise ratio because he had variability, which was like noise, and he had average, which was like the signal. So he worked out a signal to noise ratio type of measurement. And that's what is shown here. You see that little formula there? Signal to noise ratio. It is shown as with this little formula, minus 10 log y bar square divided by s square. This little formula here is an indication of the sensitivity of the system to noise, signal to noise ratio. This was Taguchi's approach. What he did was, he went along and he applied that to define various types of conditions under which you would probably need different types of signal to noise ratios. So Taguchi gave us three different formulas for evaluating signal to noise ratios once your data was collected from your robust design experiments, which is the inner array, outer array experiment. So if you had an experiment like this, or if you had an experiment like this, you take the data, you convert that into signal to noise ratios like this using one of these formulas. And that could then be plotted. And here what we have is the plot, first of all, of the average torque, then the standard deviation of the torque, and then of course the signal to noise ratio. Taguchi's idea was, if you maximize signal to noise ratio, you're getting maximum robustness. That's what he said. He said if you're maximizing signal to noise ratio, you're maximizing robustness. That was his suggestion. And of course, here we've got the main effect of basically these three different control variables, which you saw earlier. And let me just to remind you what those variables are. They are armature turns, gauge of the wire, and ferric content of the core. Once you did that, once you plotted this, you could see the main effect of each of those things, and it turns out this guy has the largest effect. This particular factor has the largest effect on torque. The higher the better, of course. But if you look at the standard deviation, it turns out this design also is a good one. It gives you a lower standard deviation. So I'm getting high torque and lower standard deviation. Ideally, this is the one I should be using. But Taguchi said what you should do is use the signal to noise ratio, and I end up with some other factors here. There is some controversy here, and many people of course say that instead of using signal to noise ratio, you should be using other approaches to achieve robust design. Still, his philosophy stands. It's very important for us to realize Taguchi gave us many new things. One, of course, is that being at the target is the best. That's number one. Number two, you got to make the product robust. This is number two. It's very, very important. Number three, to conduct experiments, you should use orthogonal arrays. Many times these turn out to be quite all right. You don't really need fancy interactions to be incorporated in your analysis. Then, of course, the fourth contribution that he made, which is where some of the controversy is his recommendation that you should be using signal to noise ratios. I have also done a lot of Taguchi experiments, several engineering experiments that involve the Taguchi method. What I normally try to do, and this of course in print also, it's in publications, is I try to drive performance to target, and I get a contour. I get a contour of design combinations, design variable contour combinations that give me performance on target. Then what I do, my second step is I go on that contour and I try to find the point that has got highest robustness. So I'm achieving target value for the performance, and also I'm achieving robustness by minimizing standard deviation on that, standard deviation of variation. I do not use signal to noise ratio. That's my personal choice. But of course, you know, we've got a lot of choice here. Once we know the purpose, once we know the philosophy, that's all we really want to. How we do it in detail is pretty well left to you and left to me. And that's what you'll find most of the time. Now, there are cases when we have gone a little bit beyond where Taguchi took us, one of which is called multi-objective robust design. Now, to get there, let me remind you of what we started with. We started with, for example, robust design as a philosophy. And this is different from sensitivity analysis, because here you are also trying to incorporate Taguchi's philosophy that things should be on target and then they should be robust. If you just do sensitivity analysis, let's say I completed the design of a product, then I vary one or two factors. One or two factors I vary, and I see the impact of that on its performance. What that really does is it just gives me one factor at a time type of sensitivity. I really am not doing robust design type of experiment when I'm really doing sensitivity analysis. So this is something you've got to remember. If you do it the Taguchi way, if you use the inner array and the outer array, perhaps what you could do is then see on what settings I'm getting target performance and which among all the designs that give me target performance I'm getting maximum robustness. If you're doing that, you're doing pretty good. Once you accept this philosophy, the method that you use is pretty well up to you. But please make sure performance is on target, number one, and number two, you get robustness. It turns out that there are examples that we can go back to. Remember the chocolate experiment. The red chocolate bar would be the molten chocolate. Those are the ones that kids would like to probably have, but moms would complain because they have to wash their shirt. And of course, kids come back with all the gooey stuff in their hands. That's not something moms don't like. On the other hand, if the design is done in such a way that the design is tropicalized, which really means it's made robust with respect to the environment in the tropics, that's in Bombay or Kuala Lumpur or Singapore or somewhere, then of course what you have to do is you have to play with the recipe. Once you play with the recipe, make sure you choose the recipe that gives you that right target. That's the kind of shall I say, plasticity that kids are going to be happy with, the real consumers of these chocolate bars. That's number one. Number two, you also got to make it robust. For that, you may have to you may have to play with the recipe. And these recipes, this playing with the recipes can be done in controlled setting using design of experiments. So that's like something that's like one approach. Let me show you another approach. I have noise. Of course, noise factor is there, and there are design factors A and B. I can combine these different design factors. I can produce different prototypes. I can subject those prototypes to noise, and I can really then do my robust analysis, robust design analysis. I could do that. This is like something that I can do quite easily. But just take a look at this diagram that I showed you a long time back. What we are really trying to do is we are really trying to see, are there frameworks available, or can we construct frameworks whereby we could do this empirical work, perhaps not using OAs, because OAs don't really give us the exact optimum setting. OAs probably don't do that. It's not very easy for OAs to reach the exact optimum or even near optimum. It's not so easy. You have to do multiple experiments, multiple rounds of experiments. Is there some method that can actually shortcut this path, can take you a little closer there? So basically what we're doing is we are saying, on this march toward knowledge, and in trying to do this empirically, we may not exactly always use the OA type of method. Let me show you a method that actually works quite well. Taguchi experiments would have required you, if you got 3 design variables, to build these 8 different prototypes. So you see 8 different chocolate bars there. Each of those chocolate bars would have then to be shaken up using temperature variation and perhaps humidity variation. And you'll probably have to see which of these bars, which of these bars first of all would meet the target performance. That's the target stiffness that I can chew on without too much trouble. Number 2, I'll also have to find out those designs that give me the target performance. Those designs, among those designs, is there one that has got the smallest sensitivity to noise? This is the one that's going to be what we call the robust design. How do we achieve that? Well, Taguchi's approach would have been this, would have been conduct the inner array experiment, bring in the outer array, shake each of these chocolates, and then work out the robust design. That would be one way. The alternate approach is this. What are we trying to do? Try to think a little bit what we are trying to do when we are trying to do the inner array, outer array experiment. In the inner array, we are searching the design space. In this case, what we've done, we searched certain spots in the design space, and that we've done by taking 2 settings for each of these design factors. So we ended up producing 8 prototypes. There's an alternate approach, and this approach comes from the inspiration that is given by Charles Darwin. And the person who worked this out in good detail was John Holland, and he came up with a technique called genetic algorithms. That's also a search approach, and that is quite different from the design of experiments approach. What you there do is you produce, like nature, for example. Nature produces, through its genetic chromosome crossovers and mutations, it produces various types of products. Products are actually living things. Some of these are pretty fragile. They are not able to adapt to the environment, and they die off. These species die off. On certain occasions, these species turn out to be pretty robust. Those are the ones that they survive. They are able to adapt to the environment, and they live on for millions of years. We know about turtles, we know about cockroaches. They have survived the onslaught of so many things. Other things have adapted themselves. They have modified their genes, chromosomes, and so on, and they have been able to basically survive in the thing. Their proteins are now quite different from the original proteins and so on. Now, this model is also there. This is also a search. We're creating various different designs and subjecting those to environmental impact. Now, what do we do? How can we utilize that in our engineering design? We'll create these prototypes as per GA guidelines, genetic algorithmic guidelines, and then subject each of these prototypes to what we call Monte Carlo simulation of the noise. So I'm producing these prototypes. I do that by GA. And these prototypes would then be a combination of some design variable settings. Then I shake them up using Monte Carlo. I shake them up using Monte Carlo, where the randomness is coming, representing basically the effect of noise. Because noise is something I'm not going to control, so I'm using a Monte Carlo sort of framework to produce this shaky noise. And I'm subjecting each of these prototypes that have been produced using GA to that thing. If I do that, I've got shaking going on for each of these prototypes, and it's not very difficult to generate a robust design using this approach also. It's been done. And this also is in publication, this also is in print, and therefore it can be seen by anyone. What the GA does, it may start with a population that is like this. It's flying all over the place, and you may have no hope really to basically come up with a good design using this. But GA goes through iterations. It evolves. Just like Darwin pointed out that we have these species, and occasionally we'll have crossovers, we'll have sexual interaction and so on and so forth, and with that we'll be able to produce new organisms. And some of these organisms, they'll also go through some mutation because of radiation, from cosmic radiation and so on. They'll go through some changes, and the genes and the chromosome would change, the position of the genes would change and so on. When that thing takes place, the proteins manifested also would be different, so you'll end up with new species. These new species, they are then subject to the environmental factors and the impact of the environment. Those that survive, they go on to become a new species. Those that do not survive, they die off. And that's what is one explanation of how Darwin thought evolution had taken place. We are trying to do the same thing there. So this is like a noisy, it's just a random creation of species. Then we subject them to the environmental things, and we keep the ones that are good. And now I've got a smaller collection of candidate solutions, candidate robust designs. Again, I subject these to basically noise, and I select the ones that survive the effect of noise. How do I go from generation 1 to generation 2? It is through these interaction between the chromosomes. So I'll take the tail of one, I'll take the head of the other, and I'll combine the two, I'll create a new organism. And the new organism will turn out to be half of mother, half of father, or 1/3 of mother, 2/3 of father, and so on and so forth. If this is how new species are created, if this is how new chromosomes are created, those can then be tested by putting them in place of the environment, subject to the environment. And then, of course, if they survive, they lead on to a new species, and will have descendants that they are well adapted and so on and so forth, and those would be surviving there. If they do not, then of course we've got problems there. So this is like one way where I could substitute that orthogonal array, which was there in this old design, by a scheme that is now using genetic logic, genetic interaction logic, and you're able to do that. Let me give you an example. Here's an example. This is an example of a engineering design. This is an engineering design that was done, and it had a lot of complications. And I'll give you an example of, give you some examples of the kind of complication we got into. Most of you, particularly those who are engineers, they have played with what we call strain gauges. Strain gauges are things which are really stuck on the bodies of various things. For example, if I wanted to find out the deformation of this bottle, as I'm touching it, I'm deforming it, and with that the diameter is changing or something else is changing, and that thing can be actually detected. Even if the deflection is very small, you can detect that with a little strain gauge that you mount on the side of this. I can do that mounting in various spots. Wherever there is a deformation expected, we can put our little strain gauges there. And that's how I really measure. I subject this object or this body or this part to some sort of a pressure, some sort of a stress, and that stress is going to cause some deformation. My little strain gauge, if it is mounted on the side of it, I can run wires from it, and I can look at the resistance of that strain gauge. And when it deforms, obviously the length of the wires inside the strain gauge, those are going to change, and therefore resistance is going to change, and therefore the manifest voltage, if I'm putting a steady current through it, then the manifest voltage is going to change, or if I'm applying the same voltage, current is going to change. So it's going to be possible for me to detect the changes in resistance as caused by deformation of the strain gauge itself, because it is mounted on the side of a body. The strain gauge is mounted on the side of a body, and this mounting will cause the gauge also to change its resistance by the deformation that might be going on with the body, with the main body itself. And by reading a galvanometer, I can then find out what is the strength of that deformation, what is the strength of the various things I can find out, because I've converted now the deformation or the stress into a deflection. Now, this is all fine. This is basically the principle of designing strain gauges. But there is a problem here, because the strain gauge is very sensitive. It's very sensitive to slight changes here and there. And suppose you're doing the experiment and you lean on the table, or somebody walks by, or somebody drags a furniture or something like that. All those vibrations also get into that strain gauge. And the deflection and the reading that you are finding, there's been a steady change. Suddenly it fluctuates. It fluctuates this way, that way, and so on. So what you have to really do, one of the things that you must do when you're using a strain gauge is to somehow dampen or reduce the effect of these low frequency changes. When some person is walking by or some person is leaning on it, these are not high frequency fluctuations. These are the ones that actually are pretty low frequency, and we should have a cutoff. We should actually, what we have to do is we have to create an electronic filter that will look at the signal that is coming out of the strain gauge, and it should remove those. It should remove those unwanted variations. Those are being caused by people walking and people leaning on the table and so on and so forth. Those are the vibrations that should be cut out of the system. This can be done if you design what we call an electronic filter, and you interface that filter between your source of the electrical signal, which is the strain gauge, and where the reading is taking place. If you put a filter in between, then only the kind of signals that must go through all the way to the reflector, only those would go through, the others would get basically chopped off by the filter. So the filter does a pretty decent job. Now these filters, very fortunately, we have enough theoretical development in the electrical sciences where we can design a factor to exact specs. But that will lead to a particular cutoff frequency. You give a cutoff frequency of, let's say, 10 cycles, 10 hertz, or 50 hertz, or 1000 hertz, or something like that. If you do that, the electrical engineer is going to sit down, he's going to be able to do some calculations, and with that he'll be able to come back and say, pick your components, those are going to be the components inside that electronic filter. Pick them to have these values, and your filter is going to work like a charm. Those calculations are possible. And I can come up with an exact design that will give me the exact cutoff frequency. That is there. But you and I, we know that when calculations are done, it's very possible that he will say some resistance R2 must have a value that is equal to 1.63 kilo ohms. He may also say I need another resistor, and that's going to be R3, and that's going to have 423 ohms. That's the requirement there. And I need a capacitor, and the capacitor must have a picofarad capacity. That's going to be, let's say, 242 PF. That's going to be the thing. Now these are the specs for the components of the electronic filter, and you see the electronic filter on the screen here. I've got R2, and I've got R3, and I've got C. These are the three design components. They are the three design parameters that I can play with. By playing with this, I can come up with any target cutoff frequency. So if I've got a cutoff frequency, some cutoff frequency omega, I can pick these in such a way that this omega can be made equal to exactly whatever you want. And we will see just in a minute what the target value is going to be. So there is going to be some target value, and that target value can be met with these things. Now suppose, as I was saying to you, suppose this has been done. An electrical engineer, he sat with his calculators, and he went through the formulas and so on, and he did all this manipulation, and he came up with R2 equal to so much, R3 equal to so much, C equal to so much, and he was able to give you a design. He says, sir, this is your design. So these are the designer's recommendation. This is the design. Now the problem is this. If I go to a store and if I say, please give me a resistor that is 1.63 kilo ohms, I'll never be able to find that because that's not one of the standard parts. If I say, give me a resistor that has got the resistance of 423 ohms, tough luck. I can't find that on the shelf anywhere. In the catalog, I cannot find a capacitor that has got the value of 242 picofarad. I just can't find it. These are not standard parts. And that actually means I'll not be able to meet this target also. So that means I've done this design on paper, but I'm not able to actualize that. I'm not able to realize that in real life. I'm not able to do that. Now suppose somehow I did something by which I was able to allow some variation here, some variation here, some variation here, some variation here, and stay pretty close to this. I allow for a variation here, I allow for a variation here, I allow for a variation here. So maybe the nearest one is 1.50. Maybe the nearest one is 400. Maybe the nearest one is 250. If I get these components, notice three different components. If I get these three components, and let me just mark them in green. This one is one, this one is the other one, and this one is the third one. Suppose I get these components, will I still get close to this? Will I still get my performance close to this? Well, luckily, Taguchi's robust design says yes, you can. You got to be slightly lucky, but generally speaking, engineers can start with a design that is like this, the exact design, that will give you the exact performance, and make the design robust. For that, you will probably have to manipulate certain things. And you can then allow this value to be slightly different from 1.63, like 1.50 here. Instead of 423, it will be 400 there. Instead of 242, it will be 250 here. You can allow these changes and still this will stay there, provided this performance has been made robust with respect to the choice of these values there. If you could do that, you've got a robust design. You've created a robust filter that will still give you that cutoff frequency that you want, and at the same time it will allow you to go to the market and buy the components that they have as standard components. This is like a big jump in terms of the utility of what is there available to us. At the same time, we are staying pretty close to whatever we wanted to do, which is like staying close to the target at which the cutoff frequency should be. Let's see how we did that. We again go back to the slides there, and I've got now two responses. One is, of course, the deflection. That's on the galvanometer. I've got to have a certain amount of deflection. That's given to me as 3 inches. That's like specified. So I've got one target that says deflection equal to 3 inches. And then I've got cutoff frequency. That also has been specified to me, and we'll find out in a minute what that is. It turns out this has to be 6.84 Hertz. That you can see is a pretty low sort of thing, and this is generally kind of vibration that you get when there are people moving around and so on. You'll get vibrations like this. And this 3 inches is the full deflection of the galvanometer. These are the two targets that we got. So you've got tau 1 here and you've got tau 2 here. I got to make sure, as Taguchi said, I got to make sure I get this performance on target, tau 1, and this performance also on target, tau 2. And we got to make sure the whole system is robust. Let's see how we go about doing this. It turns out, if you get into electrical engineering, you can find, you've got those conditions there, you've got these design values, these different component values. If you do circuit analysis, you'll be able to derive the expression for omega. You'll also be able to derive the expression for D, the deflection. These are not very difficult to do for electrical engineers. And then, of course, what I do is I set the first one. Omega is set equal to 6.84. and I set the other one equal to 3.0. Notice here the degrees of freedom I have. I have 3 different design variables in my hand that I can pick any way I want, and I have to meet 2 target values. With these 2 target values, I can manipulate. Now my design variables are the same ones. I've got R2, R3 and C. These are the 3 different variables, design variables. I can choose these in such a way that I meet this target and also I meet this target. And that I could do because of this equation. The equations which are there tell me right away that it is possible for me to find the values of R2, R3 and C in such a way that I meet this objective when I am satisfying this target requirement, and also I am able to satisfy this objective when I am meeting the reflection requirement. Notice here I have 3 variables to play with, and I've got 2 constraints, and therefore one design variable remains free, and that's the one I'm going to exploit. When I'm seeking robustness, I'm going to exploit that, and I'll show you in a minute how I do that. So I've got 2 constraints, and therefore I get 1 design factor free. What I did was, the next thing that could be done was, you build these prototypes. And of course, you don't really have to physically build them. You can get a circuit simulator. Like, for example, there are many different circuit simulators available. These are software where you can specify the circuit, you can specify the conditions. SPICE is one. And with that, you can get the performance simulated. You can get the simulated performance. You can find out by putting certain things for R2, R3 and RC, what target you're going, what value of performance you're going to get. You can derive that using SPICE. You can do the same thing for this one also. It's not very difficult to do that. So I'm able to simulate that. I'm also going to be able to simulate noise by using a little Monte Carlo. I can simulate that noise. Remember I showed you the example where the different chocolate bars were produced on paper, of course, and they were disturbed using Monte Carlo simulation. So we got the effect of noise and effect of that, all those things we could do. Now, what is it that we are trying to do? What is our objective? Our objective is twofold. One, keep our performance on target. So we got to meet this requirement, we also got to meet this requirement. In addition, we got to make this one robust and also this one robust. These two have to make robust. Now, something I've got to remind you of is when we talk of robustness, we are talking of minimizing variance. That's what we are looking for. We are trying to minimize variance, this variance being caused by noise. In our case, the noise is coming from not getting the exact values of the design variables that I would like to have in my electronic filter. In place of 1.63, I'm getting 1.50 kilo ohms, and in place of 423 ohms, I'm getting 400. So there is obviously a noise variable there, a noise component there, and a noise component there. And I have the same thing here. In place of 242 picofarad, I'm getting 250. There is also a noise component there. These I can simulate. These I can simulate in SPICE or otherwise, and I can do Monte Carlo to do that. What will that do? That will give me a variance for this target, this performance, and also a variance for this performance. This is what has been plotted here. This is what has been plotted here, and here what we have done, we've chosen R2 and C in such a way that we get the 2 targets, tau 1 and tau 2. Because these are simultaneous equations, I've been able to get this target and that target met by selecting appropriate R2 and C. The one that is left free is this one. This is the one I'm going to be manipulating to try to minimize variance. And let me show you what we saw. What was seen when we tracked the variance of omega C. Omega C is now our cutoff frequency. The variance of that corresponding to different values of R3, because R3 was a different variable. Remember, for a given value of R3, we could choose C and R2 in such a way that would meet the 2 targets, tau 1 and tau 2. So that was given, that could be taken for granted. Now all we wanted to do was, we wanted to minimize the variance of omega C, the cutoff frequency. And that could be done by just by doing a little search there. We found Around R3 value of 360, we got the best design, that's the most robust design that gave us the minimum variance. And this variance, of course, was simulated by Monte Carlo. We looked at then the deflection and the variance of deflection, and that also turned out to be quite low in certain range of R3 values. The only problem was, if you look at the value of R3, the best value for R3, that would be around 360 there, and the best value of R3, that would be around 110, somewhere there, 110, 120. When we tried to minimize the variance of RD, these two did not coincide. One was here, the other was here. So that means I really did not have enough degrees of freedom to make both the objectives. What were the two objectives? Variance of D, deflection, and also variance of omega. We could not make both of them simultaneously minimum. That was not possible. What do we do? Well, there is a thing to recognize here. If we applied the old two-step method of Taguchi, we would not be able to reach this point. We retained his philosophy, but we changed the technique. We changed the technique for doing this. When we did that, we reached what we call a globally optimum design. And let me just show you how this was done. We used a technique that is available now to people who are working with multi-objective problem, and they are doing this using genetic algorithms. We are using GA now to create robust designs. And the technique is called non-dominated multi-objective GA. The non-dominated sorting multi-objective GA, it's a special kind of GA. I'm just going to show you the flowchart for it. This is the kind of genetic algorithm, that's a special genetic algorithm. It's different from the old Holland-Goldberg type of algorithm. It's a special one. And there are a couple of books now in this area, they are available. And with that, what you're able to do is, you're able to generate what we call Pareto optimal solution. I'll give you the idea of Pareto optimality in just 1 second. Let's say I've got two objectives, and the objectives are given like this. I've got objective 1, and this could be, for example, omega c, and not quite omega c, but the variance of omega c. Variance of omega c is one objective that you'd like to minimize. And this is variance of D, the deflection, which you'd also like to minimize. So the good place to be is here. That's where you'll get the most robust design. But in actual fact, it turns out, because we've got only R3 to play with, if you change R3, you get different types of, different combinations of variance omega 3, variance omega c, and variance D. Now, these can be found using this multi-objective GA. Notice any of these points is a design. That means these are actual designs that you can create. You can fabricate these designs, and those designs, they are the ones that are Pareto optimal. P-A-R-E-T-O, optimal robust designs. Pareto optimal in the sense that what is happening here is, it will go out and it will give you it will basically give you a design that is going to be best that is possible when you vary R3, and also it's best that is possible when you try to manipulate the other variables. So I end up with minimizing this as best as I can. So I'm coming this way, and also I'm trying to come this way. And these are the best designs. If you go below this, your target values will not be met. So therefore, this is the point. These are the designs that give you the target, both tau 1 and tau 2, tau 1 and tau 2. Tau 1, remember, was 6.84 hertz, and tau 2 was 3 inches. Both of these would be met on all of these points, but as far as variance is concerned, you can't really get better than this. Identifying these is done by this multi-objective GA. The multi-objective GA will give you these fronts. They'll start somewhere here, and they'll gradually bring it down all the way, and then end up with these designs there. These are the designs that are Pareto optimal designs, and let me just show you what they look like. This is the logic of the genetic algorithm, the multi-objective GA, that actually produces the Pareto optimal solutions. That is possible to be done by this. And when you look at the solution, they turn out to be like this. These are the best designs as far as meeting the target is concerned. I'm able to meet the first of all, the first target tau 1, and the second target is tau 2. Both I'm able to meet. One is with regard to cutoff frequency, the other is with regard to deflection. And the third thing that it has done, it has minimized to the extent possible. It has minimized to the extent possible the variances. And these variances are caused by noise. Where did this noise come from? It came from not finding the exact settings of the parts, the exact values of the parts that came out in my calculation. For example, when I did my calculations, I had 423 and I had 1.63 and I had 242. I could not get these in the marketplace. Instead, I got these things. This design can use these parts, give you both of these targets, and also minimize the variance. And we've been assisted here by the genetic algorithm. That's how we've been able to produce these designs. This is a very, very powerful method. Now, the proof is obviously in the pudding. So what was done at that point was we looked at some of these designs, and we picked a few of them. We picked about 15, 20 of them, and we fabricated these designs. We fabricated these different strain gauges or the electronic filters. And these low frequency filters, after they were fabricated, we only needed to pick some value of R3, some value of R2, and some value of C. These are the performances we got. We got the average, which should be at 6.84. We got some of these values. And average D also, we got some of these values. And you could really basically pick and choose among these, and you could get them as close as you wanted to what was available in the marketplace. You got plenty of choice there. So you have a choice there, you've got a choice there, you've got a choice there. But you got to make sure you use this combination or this combination or this combination. These are the combinations that you must stick by, and therefore you'll be getting this performance on target and also this performance on target. Look at this number. It should be 3 inches. I've got 3.00347. It's pretty close to 3 inches. You won't be able to see that on the galvanometer. You also would be pretty happy if the cutoff frequency was something like 6.841. That's not so bad at all. These were done, and the variances were also measured, and we ended up with this method led to a very good design. So the references are given here, and you can probably read them on the thing. The particular method that I described to you, those are in this particular reference there, and there are a number of other methods which are also shown here. So to wrap up the story, what we've done so far is we looked at, first of all, Taguchi's new concept, how he viewed quality. He said quality has got to be on target. That's number one. Do not manage quality by looking at specifications. Do not try to do that. So when you are producing a part, make sure the dimension of the part is on target. Number one. Number two, it's got to be made sure that your performance turns out to be robust. It's very important, because then not only you'll have minimum loss caused to society, but also the product is going to be reliable in the old sense, but robust in the new sense. Robust when subjected to various types of variations. That's number one. Number two, of course. And then, of course, the third thing that he suggested to us was use of orthogonal arrays. This really cut down the number of trials that were required, because in the old days it used to be full factorial design. And that's how actually design of experiments could not become very popular. Even now, even in Six Sigma trials, many times we are going with OAs, because OAs give us the full control and a pretty decent understanding of factor effects very quickly. That's like something that Six Sigma people can also use, and they do use very, very, very frequently. And the last thing that Taguchi also suggested was the idea of signal to noise ratio. He said that should be the approach that should take to try to optimize things. And of course, I have shown you that we can go beyond that. We can hold on to the philosophy of Taguchi, which is like be on target and create a robust design. But as far as the method is concerned, you can bring in your own method. Once you accept the objectives of being on target and producing a robust design, you can bring in any kind of optimization method, any kind of simulation method, any kind of experimental method, experimental planning method. And the particular example that I showed you used genetic algorithms to produce robust designs. And these are pretty robust, these are pretty decent robust designs. These have been fabricated and they've been cross-checked to see that yes, they do indeed a big thing. Now this completes the little section that we had for Taguchi methods and robust design for you. It's part and parcel of the Six Sigma method that we are following, which is DMAC. DMAC, again, to remind you, define the problem, measure the deviation from what the customer is expecting, so produce some measurement readings there, analyze, try to understand the capability of the system and make some measurements, also make some proper measurements so that you can assist it in the analysis, and that analysis may require some statistical work. Then of course improve, and improve will require for you to harness some technique like design of experiments. That's like something very basic. And then of course the last piece is control. Once you've identified the optimum setting for the Six Sigma process, make sure the process stays there, and that you could do using SPC, statistical process control, to keep the different variables on track. This was a pretty major step, and of course we have a few more things to talk to you about under our series of lectures that are continuing on Six Sigma. So hopefully we'll be seeing you soon, and just tune in again. Thank you very much. Thank you.